Joining us, and now I'll turn it over to Rolf.
Thank you, Kelly. I say hello, everyone. Welcome and join our MPS webinar, DC Power Supply Noise Reduction and Measurement. My name is Ralf Ohmberger. I'm application engineer at MPS, and I'm located in Germany in the Black Forest area. We will talk about audible noise in DC switching power supplies. Our agenda: first, I give you an introduction. Then we talk about piezoelectricity on MLCCs, ceramic capacitors. We will see the vibration source. We compare three mechanical systems with an electrical system for a better understanding. We go over to measuring PCB noise with a microphone and a turntable, vibration frequencies and PCB vibration transfer functionality. I'll show measurements and how to reduce noise for a DC power supply circuit. Finally, a conclusion to remember the important issues, and at last, your questions and our answers. DC switching power can generate audible noise, which is often heard as a slight whistle. Where does audible noise come from and how it can be reduced or eliminated? This webinar will describe simple ways to prevent noise while measuring and designing an application. Together, we'll explore how to find common weak points in existing or planned PCB designs for DC power supply circuits. It is a common belief that multi-layer ceramic capacitors or DC power supply circuits cause audible noise, but that's not true. The noise is generated by the printed circuit board, not by the components. Here we see three MPS evaluation boards. The noise of these components, as well as the influence of the PCB size and its mounting, are examined step by step throughout this webinar. On the left, we have a 640 volt non-isolated regulator. In the middle, a 45 standard regulator, and on the right, a 60 volt. Piezoelectricity on MLCCs. When the voltage on a MLCC ceramic capacitor changes due to the piezoelectric effect, the geometry of that capacitor changes, which results in a vibration. It expands in all directions. The solder junction transfers the mechanical energy from the capacitor to the PCB. And the ceramic capacitor vibrates at all axes when an AC voltage is applied. So the ceramic capacitors are the noise stimulus. The vibration source. How does noise arise on the PCB, and which components of a DC power supply circuit are responsible? A voltage change that occurs in a ceramic capacitor generates a vibration stimulus. Vibrations are easily audible in the speech-sensitive frequency range. It goes around 100 Hz to 7 kHz. The vibration is transferred to the PCB via the solder joints The PCB then emits an audible noise comparable to a loudspeaker membrane. The figure shows the typical components in a DC power supply circuit, ceramic capacitors, and the dimensions of the PCB are key to audible noise, as other components makes no noise. You see here on the photos this DC converter, ceramic capacitor, and the PCB itself, which acts as a speaker membrane. Other typical components, THT, SMT, and the inductor. Not all ceramic capacitors behave in the same way. Only high capacity, class 2 and class 3 capacitors have the piezoelectric effect. Other types of capacitors, molded inductors, resistors, and ICs do not show any change in geometry under load. This means that other components are insignificant sources of noise. See the table. You see here the most important stimulus are the class 2 and class 3. These are the ceramic capacitors with a high ratio of capacity divided by volume, which means for example, the Z class, X5R, X7R, they are noise sources. No-noise sources are, for example, tantalum, organic capacitors, the class 1 ceramic capacitors, and the switching inductors is normally quiet. So far, it's not an open inductance. Then it can happen that it's also make a little noise. Ferrite bead resistors and the DC-DC converter itself is quiet. Very quiet. Okay, if there is much current, it makes a very little noise, but you almost don't hear it. The stimulus, in general, ceramic capacitor types with higher capacitances and volumes are affected. Damped means almost no noise. There are, for example, from Murata, there are interposer type ceramic capacitors. They are mounted on an interposer ceramic substrate, contributing to a reduction in the squealing level, such as those available, as already told, from Murata. Then the metal strip, that's the capacitor on the photo. The energy, the vibration energy is damped by the metal, and not so much energy is transferred to the PCB. A DC power supply runs in general either in FCCM or AAM. A DC power supply circuit operating in forced continuous conduction mode, FCCM, only produces audible noise within the speech-sensitive audio frequency range. For example, GSM pulses or other periodic loads. A high DC switching power frequency is not available. Of course, you can't hear 1 megahertz. When a DC power supply circuit operates in an advanced asynchronous mode, AAM, light load mode switching frequencies can be in the lower frequency kilohertz range, below 20 kilohertz, and then it's hearable. AAM switching frequencies are not fixed frequencies. They are random, which reduces audibility. AAM is only active under light load currents where there is generally no strong stimulus, and therefore it is seldom noise. Here we compare 3 mechanical systems and the electrical system. Or better said, they are all mechanical systems. Audible noise on a PCB is created the same way that sound is generated on a stringed instrument. You see on the top left photo, there's the waveform stimulus. There is a voltage change in the capacitor caused by the current change, of course. The ceramic capacitor starts with vibration. The solder bridge, the solder joint transfers the vibration energy into the PCB, and the PCB itself makes the noise. It's like the soundboard of a loudspeaker. In comparison to this capacitor system, you see the guitar. The capacitor is the same like the finger, the stimulus. The strings, they are the vibrating. And the guitar bridge transfers the vibrating of the string into the wood of the guitar. So the wood of the guitar is the same like the PCB soundboard. That makes the noise. The same like for a piano. The hammer is the stimulus. The string does the vibration, and the piano bridge, that's the wood in the middle, transfer the vibration from the string into the wood soundboard of the piano. And what you hear is in general not the string, it's not very loud. You hear the vibration from the wood. And in our system on the PCB, you hear the soundboard, the PCB. Again, on the left, you see the mechanisms, the stimulus input signal for the system. The vibration transfers force into movement. The bridge transmits the vibration into the soundboard. And the soundboard transfers the vibration into hearable sound. For the stimulus, the system receives an input signal called the stimulus. The human ear is most sensitive between around 2 kilohertz and 5 kilohertz, which is in the same range as the resonance frequency of many PCBs. The stimulus waveform is like a finger strumming a guitar or a hammer hitting a chord. It acts as a direct impulse. Many components contribute to the frequency, such as PCB resonance, the stimulus hitting the string, and the PCB resonance with audible fundamental frequency and overtones. The loudest noise occurs when a ceramic capacitor vibrates at a frequency that is equal to the PCB resonance frequency. Vibrations transfer force into movement, and ceramic capacitor vibrating in free air is not audible. The same as the vibration surface of the ceramic capacitor is too small. There is not enough energy. This motion is similar to how a vibrating instrument or string is hard to hear without amplification from the wooden soundbar. The bridge vibrations are transmitted into the soundboard. The bridge solder junction transmits vibrations. Ceramic capacitors with metal solder strips on interposer substrate damp the transferred vibration energy. And last, the soundboard. The soundboard transforms the vibration into audible noise. The PCB acts as the soundboard, comparable to the loudspeaker membrane. Here we do some experiments. We are measuring PCB noise with a microphone. You see on the photo a 9 centimeter times 9 centimeter MPS evaluation board. In my hand, I hold a plastic stick and I do a short knock on the PCB, and the microphone records the response from the PCB. The stimulus, the short knock, is like a Dirac impulse and contains all frequency components. Acoustic noise and the frequency and the resonance frequency of a DC power supply circuit and PCB mount can be measured with a microphone and a small object that provides a Dirac impulse stimulus. A good choice is a condenser microphone, which is less sensitive to the magnetic field of the ceramic capacitor than a dynamic microphone. A stick made of hard plastic or plastic tweezer can be used as a simple mechanic stethoscope to make an audible noise easier to hear. Metallic objects make a louder noise, which can help search for points with a higher vibration amplitude. But then, of course, you have to be careful because they are electrical conductible. Here we compare between a powered and unpowered microphone measurement. Shows that the PCB resonance frequency is exactly the same. Powered condition, that's the top section of the photo, of the image. The PCB is excited by an electrical signal. A 250 Hertz load step causes the ceramic capacitor to vibrate, which excites the PCB at the 3900 Hertz resonance frequency. You see on the top the 3900 Hertz, it's the small wave, and you see the 250 Hertz. That's EMC coupled into the microphone. But the 3900 is really the response from the PCB. And in the unpowered condition, without voltage applied on the evaluation board, the PCB is excited by a mechanical shock, and a short push with the plastic stick causes the PCB to vibrate mechanically at the 3900 Hertz resonance frequency. The type of excitation, whether mechanical or electrical, has no influence on the resonance frequency of the PCB. The mechanical shock test shows the acoustic behavior of a test PCB, which behaves similarly to the later series PCB, as long as the dimensions and attachment points are comparable. Now we do another experiment just with a turntable. It's a simple instrument, everybody can make it. Okay, if a piezoelectric accelerometer, which is normally the better instrument for such a measurement, is not available, a turntable is a simple alternative that can measure the exact horizontal vibration on the diamond. A moving magnet or moving coil cartridge can be used for unpowered measurements. In a powered condition, the magnetic field of the capacitor current disturbs, unfortunately, the signal. For a powered measurement, a crystal cartridge is a better choice to measure vibrations, as it is less sensitive to magnetic EMI. While the microphone measures the integral, the cartridge or piezoelectric accelerometer measures a defined point on the PCB. Just put a PCB on the on the turntable, on the Rubbermaid, and try different hammer and measure what the turntable say on the output. Here, this piece of copper has a resonance frequency of 2166 Hertz. It's a two-sided 9x9, which is supported on two sides. Because when, for example, when you support it on 3 sides or on 4, the resonance frequency shifts normally up to a higher frequency. Here we see a comparison between the microphone in red and the cartridge in blue. Microphones show a second hammer touch. It's like a mechanical prelling from the hammer, and the mechanical bounce during the hammer impact. The large cartridge amplitude shows the horizontal movement of the PCB and the cartridge with the tone arm. Both measurements show the PCB resonance frequency. The PCB here is supported on 2 sides and is free above the rubber mat of the turntable. You see in blue and in red, you see the 2166 Hertz. That's normally, for this PCB, the frequency you would hear when you have a trouble with the ceramic capacitor, when it comes in resonance with the PCB. The difference here between the microphone and the turntable is the microphone measures the integral of the noise, and the turntable only the single point exactly on the PCB. This table here lists different resonance frequencies under different conditions. You see here a small PCB, 4 centimeters up to 9 centimeters, and under different conditions. The highest resonance frequency you have on the smallest PCB size. Together, when the PCB is, for example, here it's pressed with force from my fingers lying on the turntable Rubbermaid. And the largest one with 2166 Hertz is 2 sides supported. So here you see the influence of size and support of the PCB. The target is that you shift the resonance frequency of your whole system, in best case, above the hearable frequencies. So for example, when you have 5, 6, or 7 kilohertz, then you're already very good because the ear is not so sensitive in that range. Or 10 kilohertz, you almost don't hear it. But unfortunately, 2 kilohertz, 3 or 4 kilohertz, the ear is very sensitive. During the practical design, a mechanical model of a PCB in a preliminary design status can be used for the first measurements. Mount the PCB in the housing before measuring the resonance frequency and measure both in combination. We have this very often. Our customers often say sometimes the evaluation board makes noise, but when they use the same circuit in their series, in their housing for the series type, for example, then it's quiet. The reason for that is it's another PCB, the mounting is different, and this shifts generally the resonance frequency to a higher value, and you don't hear it so good like a very sensitive range. So always test in the housing. It's the best whenever you can do. Vibration frequencies and PCB vibration transfer functionality. Calculate the fast Fourier transformation of the load currents and compare these values with the resonance frequency from a PCB model. Check whether a calculated frequency reaches the PCB resonance frequency. Frequencies in the range of approximately 1 kHz to 7 kHz are easily audible to the human ear. We see here in the image the fast Fourier transformation of a 250 Hz rectangle load step current. The fundamental or the harmonics can excite the resonance. A PCB has a vibration transfer function which approximately corresponds to a mechanical second-order resonance system. It consists of a mass and spring constant defined by PCB size and stiffness. Superimpose the FFT with the PCB vibration transfer function, then check for overlapping frequencies with the PCB resonance. Consider the mechanical design and ensure that large vibration amplitudes cannot reach the area of the resonance frequency. So to do this, you have to know where is your resonance frequency of your latest system. You can find it out with the tests, with the microphone or with the turntable. With the microphone, of course, it's much more easy. The turntable was a little bit playing. I use best the accelerometer. That's the professional instrument for that. But I don't have that in my lab because I don't need it any day. The microphone, no problem. Measure very accurate and measure your resonance frequency of the system and check if the currents hit that resonance frequency. What you can do to avoid the noise on the PCB, the best, of course, is increase the damping. You see the curve is down, the amplitude goes down, and shift the resonance to the highest frequency possible. That's normally very easily in the housing, it shifts up and the damping increased by, for example, by rubber. When you put rubber under the screws or when you use more screws to fix the PCB, it also shifts the resonance frequency to the highest frequency possible. The measurements can be done with different things. You can use a pencil, a plastic stick, a plastic tweezer, or the metal tweezer when you don't touch the hot wires. First, search for loud locations. A loud location is normally a good place for an additional fastening screw, because it damps the movement on that point. Additional fastening increases the resonance frequency, and damping material under the fastening points converts vibration into heat. That increases damping. Just the rubber under the screw helps a lot. The transfer function is becoming more flat. As already said, the microphone integrates audible noise. The cartridge measures on the diamond position. The cartridge, tone arm, and PCB are in resonance here at 128 Hertz. But you see, the blue and the red, both of them show the hearable resonance frequency of that PCB. It has here 2395 Hertz. You can try different types of hammer for the experiment. When you start such experiments, you will see what's the good tool for this job. You are very free for this, what you use. Two other measurements, the small ones, the same PCB of 4 centimeters. On the top photo, it's supported on 2 sides. And on the bottom photo, it's full on the rubber mat. You see the top scope picture, 4,552 Hertz, and on the bottom, 5,058. And you see also the damping is much more damped, and much more damp means less noise. And here is the best. The same PCB, you press it in addition on the rubber mat. You see there's almost no electrical signal, whether from the microphone or from the cartridge. Such a PCB would be quiet, very quiet. So again, the remark, audible noise will be different on the workbench when the PCB is only, and in the housing of the final product. Test audible noise when on the workbench and test it in the final housing or with a draft model of the later housing. If the series housing is not yet available, a model also helps. How to reduce noise for a DC power supply circuit? Vibrations are clearly audible around the area of the PCB resonance frequency. Avoid overlapping vibration frequencies and resonance frequency. For most PCBs, it is not possible to change the electrical excitation. However, the PCB can be changed in the following ways to avoid acoustic noise. Shift the resonance frequency of the PCB as high as possible above the vibration frequencies. More attachment points increase the PCB resonance frequency. Increase PCB damping and use mounting points with soft damping materials, for example, plastic, rubber. A smaller PCB size increases the resonance frequency. A larger area in contact with damping material increases damping and reduces audible noise. Consider other ceramic capacitor technology, for example, the interposer types or the metal strips, or use tantalum, polymer, and electrolytic. Consider mixing capacitor technology, an additional noiseless technology, bypass current from paralleled noisy ceramic capacitor, reduces ceramic capacitor current amplitude, and therefore the acoustic noise. Of course, you like to use ceramic capacitors, we too. What I wrote here is only a solution in case you have a lot of noise and there is no other chance to be free from the noise. Then think about 0.5 or 6. That's the last solution. And as conclusion, a change in the voltage on a ceramic capacitor causes a change in its geometry due to the piezoelectric effect, resulting in mechanical movement. This vibration generated in the MLCC is transferred to the PCB via the solder joints, which can audible amplify it, similar to a loudspeaker membrane. The frequency components of the vibration, the dimensions of the PCB, including its mass and spring constants, and the type of installation determine whether audible noise is generated. When developing a DC PCB mount, take care to attach the circuit board to many distributed mounting points to increase the resonance frequency. Fasten it with vibration damping materials to dampen the quality of the resonance frequency. Avoid vibration frequencies that can excite the PCB's resonance frequency. Hardware developers should consider whether audible noise on a PCB is distracting, such as on a phone or monitor in a quiet environment. Determine the frequency spectrum to be expected in the ceramic capacitor caused by the electrical load profile. Then estimate the resonance behavior of the blend assembled PCB. With this knowledge, the mechanics of the DC power supply circuit and PCB design can be optimized in advance. The methods described in this webinar can help engineers estimate whether acoustic problems are likely and save multiple developments of PCB. Now the time for questions is starting. I say thank you for listening, and now our questions are welcome. Thank you.
And there's the Q&A button at the bottom of your Zoom webinar interface. I see we have questions in there, but go ahead and add more if you have questions about the presentation. I'll also remind you that this is all being recorded, and you can find it for on-demand playback at monolithicpower.com/webinars within the next couple of days here. All right, so let's jump into the questions. So the first one was, do soft termination MLCC make less noise than standard MLCC?
Yes, that's correct. And the reason for that is there is a small damping material. I call it now electrical glue. I don't know if it is exactly glue or whatever, but this material damps the vibration caused by the ceramic, the vibration which would be transferred normally to the solder junction. So it's like a mechanical inductive, let me say it like that. There is no mechanical inductive. Yeah, rubber, it's the same, yes.
Great.
It's
And
true.
then the next, oh, sorry, continue.
No, it's okay. The next one, please.
Yeah, so the next question was, can frequency spread spectrum cause audible noise?
Which frequencies? Of course, the frequency is always the reason. The question is always if the frequency, the AC components in any capacitor, input capacitor or output capacitor of the DC-DC converter, if you hit the resonance frequency of the PCB. When you exactly hit the resonance frequency, then you have the loudest noise. And normally many PCBs, they have a sharp transfer function. They have a small area where it's a transmission of energy becomes loud. Let me say an example. For example, if you have some automotive tests where you sweep, for example, from 50 Hertz to 30,000 kilohertz with a 6 volts amplitude, when you sweep that slowly, you will always find a frequency where the PCB makes noise. But that's physics, because then you exactly found the frequency of the PCB, the resonance frequency. That's also a method to test it with a strong amplifier on the input.
Great, thank you. And then our next one, how would the resonant frequency change from a board of 2 layers to a board of 8 layers, considering everything else is the same?
It will go down, the resonance frequency, from 2 layers to 8, because you increase a little bit the mass of the PCB, because the copper has more weight than the epoxy, but normally it's not much. It's only a slight shift, because the mass of the PCB won't increase a high amount. For example, if the PCB becomes 2 centimeters larger, then you have a higher shift to a lower frequency compared to for the change from 2 layers to 8. It makes no difference. And also in general, the layout itself has no influence on audible noise, because it's really only a mechanical issue, not an electrical.
Okay, very good. I'm not seeing any other questions. This is your last chance. Type away if you have any. Oh, I've inspired someone here, Rolf. So let's see the next one. How does increasing number of vias affect the sound?
The same, almost nothing, because you don't change the mass of the PCB. Okay, you can say you change a little bit the stiffness of the PCB, but I think it makes not much difference. But when we talk about that, there is, let me explain another way to reduce the noise. If you have 2 capacitors on the output or on the input, you can place one capacitor on top and the other capacitor on bottom of the PCB, exactly on the same position. And then the vibration will cancel out a little. The movement of the capacitor on top is going in the opposite direction to the movement of the capacitor on the bottom side. And then you learned in school 2 forces which cancels out each other, which means the vibration is reduced. The only disadvantage of this method is the EMI, because you have the fast changing currents within the capacitor. You have them, unfortunately, on both sides. So this is a disadvantage for the EMI measurement. It's a matter of testing if it causes a problem or not. And the next problem is, it's not a problem, it's you have to consider it in the layout. You need more vias. You have the free play. You must have the free plays on both sides exactly on the same position. But it's a possible solution. Let the force cancel out, but has some disadvantages.
Okay, and the next one in is, how can the resonant frequency in an already made PCB be changed?
Yeah, that's it's difficult because for an engineer, he is disappointed. He is finished with the circuit. Everything is running. And the remaining problem is the noise. So what to do? You could add, for example, an additional mounting screw, but that's a new layout and another housing. You can try to add the mass. With more mass on the PCB, the resonance frequency shifts to a lower frequency. Maybe you have luck and you don't hit the resonance frequency from your stimulus, but this means you have to glue something in it on the PCB, or try it with rubber under the screws, if possible, if the mechanical designs allow such a solution. Otherwise, you must try other capacitors. For example, try the Muratas, the interposer. They are damping about, when I remember right, about 6 dBs. I'm not very sure, but try it. Then try the soft terminated capacitors too. That's all you can do. And without a layout change. This is really the worst case. That's why you should try to avoid this problem at the beginning of the design. When you really design a PCB, an application which must be very quiet in the environmental, try it before you are almost finished with your design. Make a 3D model of the housing, best in the same material, as a metal, 3D metal, when it's a metal housing, and make a small PCB of the same outline like the later product, and place there at least the DC-DC converter and let it run and listen if it makes noise or not. Of course, all these tests, they are experimental. The absolutely full professional method would be make a FEM, finite elemente calculation, but that takes time. You need the software and you need the people who can operate the software. Yes, it's a much effort. Or you can measure it with a laser vibrometer if you have one, or if you know a company who can do it. There are many ways, but here in this webinar, I wanted to show the methods who can do everybody without having very expensive special equipment.
Okay, and then the next one is, does potting help?
Packing.
Potting?
Kelly, padding? What's padding?
Well, it's potting, P-O-T-T-I-N-G.
Okay, yes, of course. This one, potting is an additional mass on the PCB, and that shifts the resonance frequency to lower frequency. In that case, you must have the luck again that the resonance frequency don't hit the FFT of your currents in the capacitor. And the potting, for example, when it's not a very hard material, when it's a little bit soft, it's damping. It's damping the amplitude of the transfer curve of the PCB and transfers vibration into heat. It should help. A very hard potting, I don't know, I have not tested it with hard potting, but with soft potting it should help. It transfer vibration into heat.
Okay, and the next one up is, would the piezoelectric frequency change much for a given MLCC from lot to lot?
The changing the PCB resonance frequency from lot to lot, or changing the frequency of the capacitor from lot to lot? What was the question?
So the question is, would the piezoelectric frequency change much for a given MLCC from lot to lot?
PCO? I don't. Can you repeat the first word? The PCO.
Piezoelectric?
What's PCO? I don't know.
Maybe look at it, Ralph. If you hit the Q&A at the bottom, you should be able to see the question. Maybe that would help.
I can imagine from lot to lot means for the capacitor, it has no influence. Only the mechanical type of the capacitor has the influence. But if the capacitor, for example, has 4.5 microfarad, or the next one 4.9 microfarad, it doesn't matter at all, because the frequency makes the noise, and the frequency is determined by the load. Okay. And the PCB itself, I think they are all behaving the same then, from the same series. They have the same mass and they have the same outline. And the PCB material is homogeneous for each of them. It's only a small shifting. And the solder quality, the bridge, the transfer from the energy into the PCB, it's almost the same for each PCB. I think it makes no difference.
Great. And then let's see the next one. Does adding different value capacitors in parallel help?
No, it don't help. I don't think so, because yeah, maybe because different capacitor means they are placed on different places, and not each position on a PCB is an excellent position to transfer vibration energy into the PCB. There can be a few millimeters away to another position. The transfer energy can be damped more or less. And when you have more capacitors, this also means you use a different capacitor compared, for example, to a big capacitor. And then it depends on the type of the capacitor. If this capacitor has a big movement of the body under AC currents, then I think it counts again if the capacitor divided by the volume is large on that capacitor, and the type, if it is class 2 or 3. You can try it, of course, but there is no general rule that a bigger capacitor vibrates less than a small one. But really, I think it's when you have more capacitors, it could be an advantage, because the current within these capacitors is shared on many positions. And when the energy is transferred on different positions, the resulting energy into the PCB should be less compared when it's only coming from a single point with a very high vibration amplitude. It could help.
Okay. And then next up, we have audible noise can come from the inductor as well. Do you have any suggestions on that?
Yes, inductor can make noise, especially the open ones when they are not molded. But from our experience, the inductor, when they are molded, they are normally quiet. And yes, this is what our experience is. Then try another inductor. It depends on the type of inductor. A molded one normally is quieter than an open one. And that's why you should use the plastic stick and touch the PCB step part by part and search for the part, which part makes the noise. And in most cases, it's the input or the output capacitor. And seldom the inductance. Of course, it makes a little noise, but not so much like the ceramic capacitors.
Very good. That looks to be the last of our questions. So a lot of good questions today. Thank you everyone for your time. If I don't see any more sneak in here at the very end, we will call this session good. Again, appreciate your time and look forward to communicating with you more in the future. Thanks, Rolf.
Thank you, Kelly. Thank you to everyone to listen. It was a pleasure for me.